Hi, today we're going to talk a little bit about optimization. Optimization, what it is, it's in the name. We're going to be given a set of restrictions or a problem, typically a word problem, and we're going to be asked to find the maximum or minimum value of something. So let's take a classic problem. Let's say we're a farmer and we need to build a fence around our field. We have 100 feet of fence and we need to encompass the maximum area possible. So we draw our field. And let's say that our field has sides of x and y. So the question is, what shape are we going to make the field if it's going to be a rectangular field in order to maximize this area on the inside? Are we going to draw a rectangle like this? Maybe we'll draw a square. Maybe we'll draw a really long rectangle. We don't know, but we can find out. So how are we going to go about doing that? That's where optimization comes into play. So the goal is to write our area in terms of x or y, take the derivative of it to find the minimum or maximum of our area function. So let's look at how we do that mathematically. So we're given that we have 100 feet of fence. So we know that 2x plus 2y is going to equal 100. Now it's 2x and 2y because there are two sides for the fence in the field. And we also know that the area of the field is going to equal x times y because it's a rectangular field. So in order to optimize, we have to solve this equation for the area in terms of either x or y, so we can take its derivative. So solve this top equation for y in terms of x. So y would equal 100 minus 2x over 2, or 50 minus x. Alright, so now we can take what y equals and plug it into our area equation. We can take the derivative and we'll be off to the races. So now our area equals 50 minus x times x. Alright, that's great. So we can rewrite our area in terms of x. We've done that. Now all we have to do is take the derivative of our area function in terms of x, set it equal to 0, and determine if we found the maximum or minimum. So that is our derivative of our area function, 50 minus 2x. If we set that equal to 0, and then we can solve for x. So 2x equals 50, and x would equal 25. So if x equals 25, we can plug that back into this equation here, and we'll find that y also equals 25. So it turns out that our field that we made to maximize the area is going to be a square. But before we determine if it's a maximum, we have to make sure it's not a minimum. So in order to be sure that the answer we found is indeed a maximum, we need to look at what the second derivative of our area function would be. So that's our first derivative. Our first derivative is 50 minus 2x. Then our second derivative will simply be negative 2. Since our second derivative is negative, that means our area function is concave down, which means that the answer we found, x is 25 and y is 25, is indeed a maximum. So it turns out that if we want to maximize the area in a square given a certain perimeter, in a rectangle given a certain perimeter, a square is the best way to go. So now we found that the second derivative is negative, so the graph is concave down. So we're pretty sure that we found the maximum, but to be absolutely certain, we need to check our boundaries. So what do you mean by boundaries? Well, this is a real world problem, so we can't have a negative fence. So x has to be greater than or equal to 0, the same way y has to be greater than or equal to 0. So if we check 0 for x in our area function, we get 0. That's obviously not a maximum area. So therefore x equals 0 doesn't produce a maximum. Now we also need to check the upper bound of our boundaries. So x can go all the way up to 50 before y gets to 0 according to our perimeter function. So if x is 50 but y is 0, our area is again 0. So now that we've checked our boundaries and we have our second derivative, we can be sure that x and y both being 25 is indeed our maximum. Let's look at another example. So, let's say we're just given an abstract problem, and we're given that the sum of two numbers has to equal 10. So let's call those two numbers x and y. So if x plus y equals 10, then we're asked to find two such numbers so that the product of one of those numbers and the square of the other is maximum. So let's call x times y squared, let's call that z. So our problem is to maximize z. In order to maximize z, we have to write y or x in terms of the other. So let's go ahead and write x in terms of y. So if x equals 10 minus y, then we can plug it in down to our z function. And z becomes 10 minus y times y squared. We can simplify that a little further, and we get 10 y squared minus y cubed. Okay, great. Now, if we take the derivative of z with respect to y and set it equal to 0, we can find the minimum or maximum. In this case, we're asked to find the maximum. So dz dy equals 20y minus 3y squared. And we have to set this equals to 0. So, if we factor out a y, we get that. Now, from algebra, we know that we can set each of those parts equal to 0. So from our factored version here, we get that y equals 0, and 20 minus 3y equals 0, or 3y equals 20, and y equals 20 over 3. Alright, well, you'll notice that at this point, we have two possible answers. So which one of them is right? Which one gives us the actual maximum? So if we plug in y equals 0 into our original equation here for z, we would get we would get 0. So no matter what x is, no matter how big x turns out to be, we're still going to get 0. So odds are that's not going to be our maximum. But let's be thorough and let's check. So let's say that we use 20 over 3. Well, if y equals 20 over 3, you can plug it into this equation here, and it turns out that x will be 10 over 3. So, if x equals 10 over 3 and y equals 20 over 3, and we plug that into this equation, we will get a positive number. Since one option gave us 0 and the other option is going to give us a positive number, it's a good bet that y equals 20 over 3 is in fact our maximum. So let's say that a company contacts you and they want you to design a cylinder for them. Let's say it's a soda can or some type of container to hold something. They tell you that the container has to hold a volume of 30 pi units. They give you the cost of the materials for the ends and the sides. The goal, obviously it's a company, they want to minimize the total cost. So our total cost is going to be the cost of the sides plus the cost of each end. There are two ends, so that's where this 2 in our cost function comes from. So let's look at how we do it. First of all, we have a cylinder. This equation for the volume of a cylinder is pi r squared h. So the area of each side, this term here, is going to be a rectangle with length 2 pi r, the circumference of our tops and bottoms, times the height of our cylinder. And that's of the sides. The area of our top, or ends, is simply a circle. So that's pi r squared. Alright, so we can start to see everything taking shape. We can see that we can write the cost function in terms of r's or h's. Let's solve everything so that it's in terms of r, so that when we take the derivative to optimize, we can just take one derivative with respect to r. So, if our volume is 30 pi, then 30 pi has to equal pi r squared h, then we can solve our volume function to get rid of our h. So h is going to equal 30 over r squared. Alright, so at this point, we should have everything we need in order to start solving and minimizing this equation here. So let's plug in some of what we had into our cost equation. Alright, so the cost is going to equal the cost of the side, which would be 2 pi r times h, but we rewrote h, so 2 pi r times 30 over r squared. That's the area of our side times the cost of our side, which is just 50. Now we have to add 2 times the cost of each end. Remember, there are 2 ends. We can't forget about that. So 2 times our 75 for the cost times the area of each end, which is just pi r squared. Alright, so let's simplify our cost equation a little bit, because it's a little hard to work with right now. Alright, so if we simplify our cost, it's going to be 3,000 pi over r plus 150 pi r squared. So, now that we have our cost function written clearly, it's clearly in terms of r, we can take the derivative of it, set it equal to 0, solve for our optimal r. So our first derivative of our cost function is negative 3,000 pi over r squared plus 300 pi times r. And that has to be set equal to 0. Alright, we go ahead and solve this equation for r, just move the negative term to the other side, we get 300 pi r equals 3,000 pi over r squared. We solve for r, we get r cubed equals 10, and r equals the cube root of 10. So now, the question is, does that answer make sense? Well, first of all, it is a positive number. The radius of our cylinder does have to be positive, so that much makes sense. And is that a minimum cost or is it a maximum cost? Well, if we take the second derivative of our cost function in terms of r, we can do that to see if it's minimum or maximum. So, this is our first derivative, then our second derivative is going to be 6,000 pi over r cubed plus 300 pi and given that our r is cube root of 10, that's a positive number. If we plug a positive number into here, our second derivative will be positive. That would mean our cost function would be concave up at that point, and that would give us a minimum cost. So we're not quite finished with the problem yet because we do need to go back and figure out what the height was. If you recall, the height was equal to 30 over r squared, which would be equal to 30 over 10 to the 2/3 power. So we have a positive radius and a positive height. We've proved that our cost is minimized, and we've just saved this company a lot of money by designing the most efficient cylinder that we possibly can.